So we'll talk about Bayesian neural networks, and we'll start by reviewing Bayesian rule for discrete random variables. So let's say we have random variables x and y, both of them are discrete. And the Bayes rule allows us to calculate conditional probability over x given y on the left-hand side, and on the right-hand side we have the ratio. On the top, we have probability of y given x, so we flip it, times the probability of x, which is called prior, divided by the total probability p of y. And to introduce the terminology, p of y given x is called the likelihood, p of x is called the prior, and p of y is called total probability or marginal. And the total probability can be calculated from the drawing by summing out one of the variables. So if we want to calculate total probability over y, it's just the sum of a joint of p of x and y, and we sum out the x. So let's look at an example of how to apply this rule. We'll look at the example of Apple Watch. In the version 4 of Apple Watch, Apple engineers introduced an ECG sensor to the device, and ECG sensor can detect arterial fibrillation. And the engineers give us the following characteristics of the sensor. So the true positive rate is 98%, and the true negative rate is 99%. True positive rate means that probability that that the test is positive, given that the person has arterial fibrillation, is 0.98, and the true negative of 99 means the probability that test is negative, given that the person does not have arterial fibrillation, is 99%. So that's the characteristic given by the engineers. But of course, as a user of the Apple Watch, we want to know probability of arterial fibrillation given the test is positive, so we need to know the flip of what engineers have told us. And we're going to use the Bayes rule for it. So this is the left-hand side. The right-hand side is probability of getting the true test given the arterial fibrillation times the prior over arterial fibrillation divided by the total probability over the test being positive at the bottom. And we know the probability of getting a positive test, probability of t given AF, that was given by the company. Probability of arterial fibrillation, the prior probability or the prevailing rate of arterial fibrillation in the population, we just get from medical literature. It happens to be around 2%. So if you pick a random person on the street and ask if you have arterial fibrillation or not, or test this person for arterial fibrillation, in 2% of the cases, a random person will have arterial fibrillation. So we need to calculate the bottom part, the total probability of observing a positive test, probability P of t. And just we're going to use this formula. It's we're going to sum across all possible values of arterial fibrillation. We're going to sum it out. So it's probability of test positive and arterial fibrillation plus probability of test positive and no arterial fibrillation. And we're going to write both of those terms as conditional distributions rather than joint distributions. So probability of test given arterial fibrillation times probability of arterial fibrillation plus probability of arterial fibrillation test given no arterial fibrillation times the probability of no arterial fibrillation. And we know pretty much everything in that equation. We know the t given AF, and we know the probability of AF. Now, probability of t given not AF is just 1 minus probability of no t given not AF. And this happens to be 1 minus 0.99. And probability of not AF is 1 minus probability of AF, which is 1 minus 0.02. So we know everything we need to know in that equation. And if you just plug this in, you get 66%, around 67%. Probability of arterial fibrillation, given the test is positive, is around 67%. Let's look at the case when we have continuous variables, and we're going to change notation slightly. Instead of x and y, we're going to use theta and y. And theta typically represents parameters of a model. So in the case of neural networks, theta is just a tensor of the weights and biases. So you can imagine taking all of those weights and biases of all of the layers of your neural network and putting them into one big sequence of tensors, and we're going to call it theta. And y is the observed data. So that's what we use to train the model. Now, in the Bayes approach, we're going to estimate probability of theta given y. So we will estimate the distribution over the set of the parameters of the model given the data and compare it to the maximum likelihood approach that we used before when we try to maximize the likelihood or minimize the loss function. And we get what is called the point estimate. So we just get one value of theta that comes out of this maximum likelihood estimation procedure. On the other hand, in the Bayesian procedure, we have the whole distribution of the parameters of theta. So you can think of this as we have a whole family of possible neural networks that is represented by different values of the parameter theta. And this reflects a couple of things. So one thing is that our data can be noisy, or our data can be not representative. So what we want to do, we want to account for the fact that the model that we find from the data might not be correct once if you use maximum likelihood estimator, who tells you that this specific value is the correct value. We say, okay, maybe we don't really know what's the true value, and instead of trying to lock ourselves into using this specific value of parameter theta in this specific neural network, we say, okay, we actually have a distribution of a parameter theta. We have a whole bunch of those neural networks, and we think that one of them is correct. And we weight them, and essentially the probability over theta given y, the posterior probability, gives us the weight over possible models. So the higher the probability over theta given y, the more likely we think that this is the correct model. But what we do, we don't disregard any model, so we keep everything as a possibility. We just assign the weights. And the Bayes rule looks exactly the same in the continuous case when theta is not a discrete variable. So we have p of y given theta times p of theta at the top divided by the total probability over the data p of y at the bottom. And p of y given theta is just the likelihood, probability of observing data given the parameters of the model. That's something that we use for maximum likelihood estimation. We maximize this specific value. But in the Bayes rule, we actually combine it with a prior p over theta. That's what we have on the top. And we have to normalize to get the proper distribution, and we divide by the total probability p of y. Now, the total probability p of y, since we deal with continuous variables theta, they're not discrete anymore, so we replace the summation with integration. We have total probability is just joint probability of y and theta, and we have to integrate theta out, or we can rewrite it as a conditional, so it's p of y given theta times p of theta, and you integrate theta out to get the total distribution over p of y. And so this p of y calculation of total probability that involves this integration is usually the hardest part of doing the Bayesian inference, of calculating this posterior distribution over theta. And for certain combinations of the prior p of theta and the likelihood p of y given theta, we can calculate this analytically. And whenever it's possible, we say that p of theta is a conjugate. For example, when both p of y given theta and p of theta are normal, we have a product of two normal densities, which is actually is another normal. So we have a conjugacy case, and things are analytically calculatable. However, in most of the practical cases, the conjugate priors are not a good description of the data or not a good description of the model, because you really have a very limited choice of priors and likelihoods to guarantee the conjugacy, and this limited choice is typically not practical. So in a lot of the practical applications, we do not have analytical solution, and we have to numerically calculate it somehow. And given that parameter theta is very high dimensional, so we talked about the neural networks, for example. In neural networks, we can be talking about millions of billions of the parameters. So calculating high dimensional integral is very computationally expensive, and it's actually if you do it naively, it's impossible. And we're going to talk about a few ways actually to do those calculations. So one way is Laplace approximation, when we approximate the posterior distribution with normal distribution, and they just need to calculate mu and sigma parameters of that distribution. Then Markov chain Monte Carlo, which is a sample-based approach, and variational inference. But we'll start about talking about numerical procedures by talking about Markov chain Monte Carlo, or MC for short.